In this video, we'll be looking at electrical actuators. And electrical actuators we see everywhere. They're very, very common, and they take a number of different types. And so the fundamental technique behind electrical actuators is we've got some coils of wire, we pass a current through them, and doing so we create a magnetic field. Essentially it's an electromagnet. And that magnetic field will move ferromagnetic material. So if we put a magnet near it, we can either attract that magnet to our magnetic field, or to our coil of wire that we're running current through, or we can repel from that magnetic field. And so we can actually move that ferromagnetic material in an attraction or repulsion sort of way. Now there's quite a few different common electronic actuator examples. Things like stepper motors that move in a revolute form. Things like brushless motors, once again, move in a revolute pattern. They're rotational actuators. And DC motors, they're rotational as well. We've also got solenoid, which move in a linear sort of motion or a prismatic sort of motion. And we can have things like a motor connected to a screw thread that we looked at previously, where we've got revolute motion turning into a helical form. And so these sort of actuators are what we use now, linear actuators. They're driven by a screw thread. The first type we'll look at are DC motors, and these are very simple. Essentially we have two different terminals applied to them and allow us to apply a DC voltage there. If we reverse the polarity of the terminals, it reverses our motor direction. And what we have is a commutator which supplies current to the coil, and it keeps reversing the direction of the current supplied to the coil. And hence we can get our attraction and repulsion happening. This sort of DC motor, and we see a very sophisticated example of one there, with gearboxes and feedback associated with it as well. It's the sort of thing that we find in a wide variety of applications. Everything from cordless drills through to kids' toys and things like that. Whole range of different DC motors that allow us to power things just with these two different terminals, and we control the polarity and the amount of current that we pass into these to control the speed and torque associated with them. In terms of advantages, they're pretty good for speed and torque generally, and they're very, very simple to control. Essentially, if we only want to drive in one direction, we just need a single FET or something like that to drive it, or otherwise a H-bridge to drive it in forward and reverse direction. In terms of disadvantages, what they really need for good control and to know where we are is some sort of closed loop control, and they need feedback associated with that to know how much they've turned. The other thing is, with that commutator in there, they're very electrically noisy and can induce lots of electrical noise onto our voltage supply line. And depending on our application, that may be a real nuisance and require significant filtering associated with it to remove some of that. We also have stepper motors, and stepper motors are similar to DC motors in that they have magnets and are driven by electromagnets. But here, rather than having our electromagnets at the center of the motor and driven by a commutator, the magnets are on the outside. The electromagnets are on the outside, and the inner magnet is on the core that's turning around. So we have a series of coils. The motor that we've got there is a 4-coil motor. And we energize those coils, or we pass current through them, and we use that to turn the position of the core of the magnet. And we do that at a stepwise sort of motion. So each time we do it, we go increment a step at a time, a step at a time, a step at a time. We can also do half steps and quarter steps and micro stepping as well by energizing multiple coils at different times and by different amounts. So these are widely used in CNC sort of machines and pick and place sort of machines where we're moving things around. Widely used in things like 3D printers as well, and robotics, where we want to know and have some sort of feedback of where we've actually moved. And if we're using single step modes and things like that, these stepper modes have a fair bit of holding torque as well, so it's quite difficult to move against them. They're not very compliant in that sort of regard. Having said that, very, very widely used. In terms of advantages, well, we have quite a few of them. Firstly, they're brushless, so we get less electrical noise associated with them. And so there's less sparks and less wear associated with having to replace commutators and replace bushings and things like that that are up against the motor. They're also very easy for digital control. We can interface them directly and basically switch directly based on the number of steps we want to move. If we want to move 130 degrees or something like that, we can work out how many steps that is and put that precisely there. And they're fairly accurate as well, even with this sort of open loop control. We can sort of get accuracies in the order of 1.8 degrees per step. That's fairly common. We could gear that down to get even higher accuracy as well, if we wanted something higher accuracy at the output. One of the other advantages is the error doesn't add up over time. It's non-cumulative. And so each time we do another step, it locks into that next step. As I mentioned before, they actually have a decent holding torque if we're continuously driving them. The disadvantages behind them though are, firstly, if we're using just open loop control, we might have movements occurring, but we might actually lose the position. We might have some slip that's occurred because the motor's stalled or something like that, and we haven't actually detected that motion because we haven't had any feedback on the shaft of the encoder. They have a decent amount of torque, but not super huge amounts of torque, and so we wouldn't use them for driving a cordless drill or something like that. Partly because of the torque, but partly because they're also fairly slow. They can also induce a bit of vibration to the system, because remember they're stepping a step at a time and then stopping. Vibration can be induced into this system, and we may need to have some decoupling of there to try and reduce the vibration that these induce into our frame or into our system that we're driving. Now, stepper motors are a type of brushless motor. They don't have brushes and commutators and things like in the DC motors, but they're normally configured to be used in a stepping sort of mode. Step, 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 and you won't precisely know how many steps. And typically when we're talking about brushless motors, we're talking about a system where our coils are fixed and our permanent magnets are what's actually moving. There's a few different configurations we can have here, where we can have the magnets between the coils, which we call an in-runner design, or around the coils, which we call an out-runner design. We've got the different pictures of both of them up there. Stepper motors aren't the only type of brushless motor. There's quite a few different types, and these sort of motors that we have here are commonly used in model aircraft and things like that, where we need very fast acceleration and high speed and high reliability when we don't have so much wear and less electrical noise. Here we can use Hall effect sensors to internally work out the position of the rotor, and we can adjust our switching that's occurring and which coils we're switching on a particular point of time based on the position of what the Hall effect sensors have measured where the motor actually is. Because of this feedback that's actually occurring, they're a bit trickier to drive, and we need multiple phases. We can't just apply DC voltage to it. We need to energize each of the coils and energize them in an order, and we need to energize them based on the speed that the motor is actually turning at. But they do give us nice smooth motion. Rather than the step motion that we have in our stepper motors, they just seem to turn continuously and very, very fast, and thousands of RPMs we're talking with these brushless motors compared to much, much slower speeds with our stepper motors. Another type of electrical actuator that we have is a solenoid. And solenoids are essentially electromagnets once again that when we energize a coil, we pull a rod or a slug into that actual coil. We attract it to itself and it pulls it back. And when we stop energizing the coil, when no current's flowing, a spring will move that back into the place that it was before. So it essentially forms a prismatic joint, a linear joint that we can move in and out. Now essentially with these, unfortunately we don't have fine control, so it's either on or off, in or out. We can't kind of do it halfway very easily. And they are an inductive device, so they create a significant electrical spike when we de-energize our coil and the magnetic field collapses, and so we need some way of capturing this. And we typically have a little snubber diode or something across there to take in this electrical field that's been generated as a result. Servo motors are another electrical actuator that's commonly used. There's a few different types of servo motors. The picture that we have there are very expensive and very high precision and high speed servo motors. And they have an inbuilt and they're controlled via a closed loop feedback system. An encoder we connect to our shaft, and that provides the feedback, and they give us very, very precise control, as you'll see in a moment in the videos that we've got there, and a very high precision, particularly when we're using them in industrial components, industrial sort of environments. Now they have feedback, so they're used for much higher accuracy applications than our stepper motors would be used, and give very high speeds compared to what our stepper motors are able to provide as well. Now you'll probably also hear of servo motors referring to these as well. And these are often called, in contrast to the other stepper motors that we just looked at, hobby servos. These are very cheap and they're non-industrial servo motors. Cheap, we're looking here at tens of dollars compared to hundreds or thousands of dollars compared to the industrial ones. And they typically have much lower speeds associated with them and a whole lot less flexibility. They're commonly used for small robotics or remote control applications where we just want to move things about, commonly used on model aircraft and things like that as well. They have a rotational output and it's got a closed loop feedback system inside that uses a potentiometer. So not particularly high accuracy, especially not compared to the servo motors that we looked at previously. They give us decent accuracy at a very low price. They typically have a very limited angle associated with them as well. So 170 degrees moving direction is fairly common for the sort of range of motion that these actually have.